Now we want to convert the max terms into min terms. So in this question, we are having 4 variables A, B, C, D. And since it is max terms, it is written in capital letters. So if you are having 4 variable, then you will be having 16 combinations or 16 numbers you can write, that is from 0 to 15. So in general, you are having, if you are having n variables, you will be having 2 to the power n combination or 2 to the power numbers you can write in binary. Now here, of this numbers from 0 to 15, they have given some numbers in max terms. That is, numbers are 1, 3, 5, 7, 9, 11, 13 and 15. So the missing numbers are 0, 2, 4, 6, 8, 10, 12 and 14. These numbers are missing. So these numbers are the min terms. Now, so these are the given numbers. These are the max terms. Max terms will be using capital M and will be using product. Then the missing numbers we already find out. So we are writing in SOP. Min terms means SOP. So we have to use the symbol summation and you have to use the small m, and we have written the missing numbers. Now we are going to simplify the 3 variable expression using Boolean algebra. They are telling us to reduce the given expression using Boolean algebra. In this question, they have clearly given that there are 3 variables. In some question, they will not give the number of variables. Simply, they will give the expression. If such cases are there, how to find out the number of variables? So first you have to check the numbers and you have to take the largest number in that given question. So here the largest number is 7. To represent 7 in binary, we need how many bits? Minimum we need 3 bits, that is 1, 1, 1. So the number of variables here is 3. Okay. But here no problem. The clearly given the number of variables as 3. Similarly, while taking the variables, either you can take it as ABC or XYZ or PQR. It is depending upon our wish. So unless given, in some questions they are given the variables as WXY or PQR or ABC. If they are given the variable, you have to take the same variable. If not, you can choose your own. Now they have given this is the given question. So how many variables? 3 variables. First, what we are doing is we are going to convert all these decimal to binary. The binary value of 1 is 0, 0, 1. So if you want, you can take, since it is 3 variable, 4 to 1. So 3 means in the place of 2 and in the place of 1 you put 1, in the next you put 0. 5 means 4 plus 1 is 5. In the place of 4 and in the place of 1 you put 1 and 0. Then 7, 4 plus 2 plus 1 is 7. So 1, 1, 1. So we have converted this decimal to binary. And this is SOP and this is min term. So the variables what we have taken is A, B, C. So if it is 0, then it is A bar. If it is 0, then B bar. 1 means C. Next one, A bar, B, C. Then A, B bar, C. Then A, B, C. First you have converted that into binary, then we have written the expression. Now from first term and second term, we are checking whether there are any common literals. The literal A and C are common in the first 2 terms. So we have taken it common. So that In the first term, B bar is there. In the second term, B is there. So the remaining will be getting B bar plus B. Similarly, from the third term and the fourth term, we are taking AC common. In the first term, B bar will be remaining, and the second term, B will be remaining. So, while studying Boolean law itself, we have studied that A plus A bar is 1. Similarly, B plus B bar is 1, C plus C bar is 1, anything is 1. So, instead of this, we have to put 1. So 1 plus A is A. So A bar C into 1 is A bar C. So from these two, I have taken C common. So here A bar is remaining, here A is remaining. A bar plus A is 1. So we'll be getting C as the answer. So C is the, so we want to convert the given expression into minterm using complementary property, and we have to simplify the expression, and we have to simplify this expression using Boolean algebra. First we have to change the given expression into minterm, that is you have to convert it into SOP by using complementary property. Now the given question is in POS. Why? Because you are having capital M and pi. And in the given question, the highest number is 7. So to represent 7, we need minimum 3 bits. So with the 3 bits, you can write numbers from 0 to 7. That is 2 to the power 3 is 8. So 0 to 7 is, you will be getting 8 bits. So of these 7 numbers, the number 3, 5, 7 are given in the question, and they are max terms. And we have to find the minterms, the remaining numbers, that is 0, 1, 2, 4, 6. These are the minterms. So from the given question, we have found out the minterms. So after getting the minterms, what we are doing is we are converting this decimal numbers to binary, and after since it is minterm, first you take A. So in minterm, this is A bar, B bar, C bar. Similarly for 1, A bar, B bar, C. Similarly for 2, A bar, B, C bar. So we have written the Boolean expression for this minterms. After that, we are in the question they have asked us to simplify the given expression. So we are analyzing this expression for simplification. While analyzing the first, in the first two terms, that literals A bar B bar is common. In the first two terms, the literals A bar and B bar is common. In the, then we are comparing the terms 3 and 4. In the third term and fourth term, here you are having A bar, here you are having A. Similarly, here you are having B, here you are having B bar. Here you are having C bar, only one literal is same. Now we can compare the fourth and fifth. Here you are having A, here you are having A. B bar, B not, right? C bar. Two variables are same. So we are going to take A bar, B bar common from first two term, and A, C bar common from last two term. So we have taken A bar, B bar common from first two terms. So here C bar is left and here C is left. In the last two terms, you have taken A, C bar common. So here B bar is left, here B is left. C plus C bar is 1 and B plus B bar is 1. So we are getting like this, A bar, B bar into 1, plus we have written the third term as it is, and A C bar into 1 is A C bar. Now we are going to take A bar common from first two terms. From the first two terms, we are taking A bar common. When you're taking a bar common from the first two terms, remaining what you're having is b bar plus b c bar. So this is of the form a plus a bar b. So in the place of a, you are having b bar. In the place of a bar, you are having b. So a plus a bar b is equal to a plus b. Similarly, b bar plus bc is equal to b plus c bar. So a bar into b plus c bar. Now you are multiplying. So a bar b bar plus a bar c bar plus a c bar. Now from the last two terms we are taking c bar common. From the last two terms you are having taking c bar common. So here you are having a bar and here you are having a. So a plus a bar is 1. So 1 into c bar is c bar. So finally you are getting a bar b bar plus c bar. This is the answer. Implementation using Nand gates. So now we are going to implement a SOP function using Nand gates. How we are going to implement? Now we are having an expression. We are having an expression. We are having an expression f3 is equal to x y bar plus x bar z. So in order to implement in NAND gate, what we are doing is we are complementing the given expression twice. So this expression we are complementing twice, that is x y bar plus x bar z. We are complementing twice. So we know that if you are complementing any variable twice, it will not change. That is a double bar is a. After that, what we are doing is we are applying De Morgan's law. So this is A and this is B. So it is A plus B the whole bar. A plus B the whole bar is equal to A bar into B bar. Already you are having a bar. So we are complementing twice, that is involution. Then we are applying De Morgan's theorem and then we are implementing that using NAND gate. So our expression is x y bar plus x bar z. So what you are doing? First you are complementing the equation twice and then you are applying De Morgan's, then you will be getting like this. So first x y bar you are giving it to a NAND gate. So this one. Then again x bar z you are giving it to a NAND gate. Then again you are giving it to another NAND gate. So it is nothing but x y bar x bar z the whole bar. This is one NAND gate, this is another NAND gate, and this dot and this another NAND gate. So we are implementing using NOR gate. How you are implementing the POS function using NOR gate? The same. You are complementing it twice, then you are applying De Morgan's theorem, and then you are implementing. So this expression x plus y, the x plus y bar the whole bar plus x plus z the whole bar you have complemented the given expression twice. This is one NOR gate, this is another NOT gate, and next another NOT gate. So you have implemented using NOR gate. Now next implementation of SOP expression. So if you want to implement anything in anything using NAND gate, then the expression must be in SOP. So this is an sum of product expression. So this is a sum of product uh, logic diagram. So in order to implement in using NAND gate, so you need a AND OR circuit. Then what you have to do is you have to add bubbles to the outputs of AND gate and to the inputs of OR gates. So you have to add bubble to the outputs of AND gate and inputs of OR gate. Then you have to replace this OR gate with the input inverted input with NAND gate. Why? Because by De Morgan's law, it is saying that A bar plus B bar is equal to A into B the whole bar. This is nothing but the NAND gate. This is nothing but the OR gate with the inverted inputs. Next is implementation of POS. So using NAND gates. NAND gates. If you want to, if you sorry, NOR gates. If you want to implement anything in NOR gate, then the expression should be OR AND. So if you want to implement anything in NAND gate, the expression should be in AND OR. If you want to implement anything in NOR gate, then the expression should be in OR AND. Now this is a logical diagram of OR AND circuit. Here what you have to do is you have to put bubbles to the output of OR gate and you have to put bubbles to the input of AND gate. Then you have to convert that AND gate with the input inverted inputs to NOR gates. Why? Because A bar into B bar is equal to A plus B the whole bar. A plus B the whole bar. Next one is positive logic and negative logic. In logic gates, usually high voltage, it is represented by 5 volt and it is 1. For low voltage, we will be using 0 volt and it is 0. This is called positive logic. However, there is another logic called negative logic. In the negative logic, high voltage will be represented by 0 and low voltage will be represented by 1. This is nothing called negative logic. So in positive logic, enable means 1. When you are giving high signal, it will be enabled, and when you are giving low signal, it will be disabled. But in the case of negative logic, if you are giving low signal, it will be enabled, and if you are giving high signal, it will be disabled. This is negative logic and this is positive logic. Next, we are going to see the topic binary codes. Now, what is binary code? So digital data is represented, stored and transmitted as group of binary digits. So data is represented, stored and transmitted as group of bits. This group of binary digits is known as binary code. They represent both numbers and letters of alphabets as well as many special characters and control function. So these codes, they will represent numbers, alphabets and special characters and control functions. Now, classification of binary codes. So binary codes are classified into weighted codes, non-weighted codes, reflective codes, sequential codes, alphanumeric codes, error detecting and correcting codes. So we are having 6 codes, types of codes, that is weighted codes, non-weighted codes, reflective codes, sequential codes, alphanumeric codes, error detecting and correcting codes. Next one is, this is codes that we can classify into weighted codes, non-weighted codes, reflective codes, sequential codes, alphanumeric codes, and error detecting and correcting codes. So weighted codes, binary and Bcd. These are weighted codes. In Bcd, there are many types of codes, that is 8421 code, 2421 code, 3321 code, 4221 code. Similarly, many types of codes are there. And this non-weighted codes are XS3 code, gray code, 5-bit Bcd codes. These are non-weighted codes. Reflective codes are 2421 code, 5211 code, XS3 code. These are reflective codes. And sequential codes are 8421 code and XS3 code. Alphanumeric codes are ASCII code, EBCDIC code, and Hollerith code. This error detecting and correcting codes are parity and Hamming code. Parity code and Hamming code. Now, what is weighted codes? In weighted codes, each digit position of the number represents a specific weight. So in weighted codes, each position will be having a weight. So 8421, 2421, 5211. These are the weighted codes. Now non-weighted codes. So in non-weighted codes, that particular position will not be having any weight. So example of non-weighted code is XS3 code and gray code. These two are non-weighted codes. XS3 code and gray code are non-weighted codes. Next is reflective codes. So what is reflective code? A code is said to be reflective when code for 9 is a complement for code for 0. So the code for 9 will be the complement of the code for 0, and the code for 8 will be the complement of 1, and the code for 7 will be the complement of 2, and the code for 6 will be the complement of 3, and the complement and 5, the code for 5 will be the complement of 4. 2 4 2 1 5 2 1 1 and XS3 are so 2421, 5211 and XS3 are reflective codes. But 8421 is not a reflective code. So this code is nothing but 5211 code. So what is reflective code? The code for 0 will be the complement of the code for 9. So the code for 0 is 0000. So what is the code for 9? 1111. Clear. Now the code for 1 will be the complement of code for 8. Here you are having 0, here 1. Here 0, here 1. Here 0, here 0. The code for 1 will be the complement of code for 8. Here 0, here 1. Here 0, here 1. Here 0, here 1. Here 1, here 0. So the code for 0 will be the complement of the code for 9, and code for 1 will be the complement of code for 8. So this is nothing called reflective code. Next, sequential codes. In sequential codes, each succeeding code is one binary number greater than the preceding code. So the one binary number greater will be having, each succeeding code will be having one number greater than the preceding code. This 8421 and XS3 are sequential codes. So first we in 8421 you put 8421. In 8421 for 0, this is 0. For 1, you have to put 1 in the place of here, 0, 0, 0. 2 is you have to put 1 in the place of 2, then 0, 0, 0. 3 is you have to put 1 in the place of 1 and 2, then 0, 0. Now in 8421 code is a sequential code. What is sequential code? Each succeeding code is one binary number greater than the preceding code. What is this 0? What is this 1? So this code is one binary number greater than this code. What is this? This is 2. So one binary number greater than this 1. So what is this? This is 3. So this is one binary number greater than this 2. So each succeeding code will be is one binary number greater than the preceding code. Okay, this is sequential code. Two four two one and 5211 are not sequential codes. Next one is alpha numeric code. From the name itself, you can understand it will be having alphabets as well as numbers. So it is called alpha numeric codes. This code consists of both numbers and alphabets. So it is called alphanumeric codes. This ASCII and extended binary, coded decimal, HISI and Hollerith code are alphanumeric codes. Next is error detecting and correcting codes. EBCDIC is extended binary coded decimal and Hollerith code are the alphanumeric codes. Now error detecting and error correcting codes. When digital information in the binary form is transmitted from one circuit or a system to another circuit or system, error may occur. So when you are transmitting the digital information, there is a possibility of error. Error means the signal will change from 1 to 0 or it may change from 0 to 1 due to the presence of noise. So in order to maintain the data integrity between transmitter and receiver, extra one more bit is added to the data. So these extra bits allow the detection and sometimes the correction of error in the data. So these extra bits what we are adding, it will allow to find the errors or detect the errors, and sometimes it will also use to correct the errors. The data along with the extra bits, they form the code, that is error correcting and error detecting codes. Codes which allow only error detection are called error detection codes, and codes which allow only which allows error detection and correction are called error detecting and correcting codes. Binary coded decimal. So it is a numeric code. This binary coded decimal is a numeric code. In BCD, each number is represented by a 4-bit binary number. So in BCD, it is a numeric code, and in BCD, each decimal number is represented by a 4-bit binary number. Now, so first we will see the difference between binary and BCD. I am taking the number 10 or I am taking the number 12. So in binary, the value of 12 is 1, 1, 0, 0. How we are writing means we have to write 8, 4, 2, 1. So what is the value of this number 12? So you have to put 1 in the place of 8 and in the place of 4. So we will be getting 1, 1, 0, 0. Now we are coming to write the value of 12 in BCD. So in BCD, what we are doing is we are splitting this number into 2. So this 2 we are writing by 4 bits in binary. So the value of 2 is 0, 0, 1, 0. and the value of 1 is 0, 0, 0, 1. So in binary, the value of 12 is 1100, and in BCD, the value of 12 is 0001 and 0010. So in BCD, each number is represented, each decimal number is represented by 4-bit binary number. Next, the disadvantage of BCD. BCD code have less efficiency than pure binary number. Advantage of BCD code is conversion from BCD to decimal is very easy. So the advantage of BCD is conversion from BCD to decimal is very easy than compared to other code conversion to decimal. Next is we are going to see Bcd addition. So add two Bcd numbers using ordinary binary addition. So if you want to add two Bcd number, what you have to do is you have to add those two numbers using ordinary binary addition. If the sum what you are getting is equal to or less than 9, then no corrections are needed. The sum is in the proper Bcd form. So if you want to add two Bcd numbers, what you have to do is simply you have to add those two numbers in binary and we will be getting the sum. If that sum what you are getting is less than or equal to 9, then no corrections is needed. The sum is in the proper Bcd form. If the sum 4-bit sum what you are getting is greater than 9, or if you are getting a carry while adding, then we have the sum is invalid, and to correct the invalid sum we have to add a 6 to the sum what you have got. So if a carry result while we are adding 6 to the sum, that carry should be added, we have to add that carry to the next higher order BCD digit. So I will explain BCD addition once more. So what you have to do means first you have to convert that BCD numbers into binary, and we have to add the numbers using ordinary binary addition, and you will be getting a sum. You will be getting a for example, you are adding two 4-bit numbers, and you will be getting a sum. If the 4-bit sum what you are getting is less than or equal to 9, then no corrections is needed, and that sum is in the proper BCD form. So while adding, if you are getting a number greater than 9, or if you are getting a number or you are getting a carry, then the sum is invalid and it is not in a proper BCD form. Then in order to correct the invalid sum, you have to add a 6, 0, 1, 1, 0. So while adding 6, if you are getting a carry, then you have to add it to the next higher order BCD digit. Now we are taking two numbers. This number is nothing but 6 and this number is nothing but 3. So next we are going to see Bcd addition. In Bcd addition, what we are doing is we are adding that two Bcd numbers using ordinary binary addition. So while adding the, two Bcd numbers using ordinary binary addition, you will be getting a sum. The sum what you are getting is equal to or less than 9. That sum is in a proper Bcd form. So no correction is required in that sum. So while adding, if you are getting a number greater than 9, or if you are getting a carry, then that sum is not in a valid form. It is invalid. So in order to change that sum into a valid form, you have to add 6, that is 0, 1, 1, 0 to the sum what you already got. While adding this 6 to your sum, and if you're getting a carry after that, then that carry should be added to the next higher order BCD digit. Now we can take, we are taking two numbers 6 and 3, and these two are the BCD numbers, and these two numbers we are adding by using ordinary binary addition. 0 plus 1, that is 0 plus 1 is 1, and 1 plus 1, 1 plus 1 is equal to 1, 0. This 0 is sum, and this 1 is carry. So this is the sum and this is the carry. Then again we are adding 1 plus 1. 1 plus 1 is 1, 0. The 0 you are writing here, the carry, your 1 plus 1 is equal to 1, 0. The sum you are writing here and this carry you are writing here. So here, that is 1 plus 0 plus 1 is 1. So you are getting number 9. This 9 is equal to or less than 9. 1001 is less than is equal to 9. So this sum is is valid and no modification is required here. Now next we are adding 8 plus 6. So we are adding 8 plus 6. So we are going for ordinary binary addition. So 0 plus 0 is 0. 0 plus 1 is 1. 0 plus 1 is 1. And 1 plus 0 is so this is the sum what you are getting 1, 1, 1, 0. So this number is greater than 9. So the sum is invalid. So in order to make this sum valid, we have to add a 6. So we are taking this number and we are adding a 6. So 0 plus 1 is 0. 1 plus 1 is 1, 0. 1 plus 1 is 1, 0. You are writing 0 here and you are writing the carry here. So 1 plus 1 plus 1 is 1, 1. So here you are writing the sum 1 plus 1 plus 1 is 1, 1. So you are writing the 1 here and the carry you are writing here. So 1 plus 1 is 1, 0. You are writing the sum here and here you will be getting a carry. That carry is this one. So you are getting an extra number. So what is 8 plus 6? 8 plus 6 is 14. So in 14, if you are writing in BCD, you will be getting 0, 0, 0, 1. And for this 4, if you are writing in 4 bits, you will be getting 0, 1, 0, 0. So this is 14. This is 1 and this is 4. So we are getting we are adding 8 and 6 and we are getting a number 14 and it is greater than 9. So we are adding a 6 to that number and here we are getting we are adding a 6 and we are getting the 14. That is nothing but 8 plus 6 is 14. This is the BCD value of what? 14. So here you can add zeros. If you add 3 zeros, it will become 1 and here you are getting 4. So this is nothing but 8 plus 6 addition in BCD. Next. Next we are going to add 9 plus Next we are going to add 9 plus 8. This is 9 and this is 8. Ordinary binary addition. 1 plus 0 is 1. 0 plus 0 is 0. Again 0 plus 0 is 0. Then 1 plus 1 is 1, 0. So you are adding two 4-bit numbers and you are getting a 5-bit. This extra bit is nothing but carry. So already I have told that when you are adding two BCD numbers using ordinary binary addition, and if you are getting a carry, that carry, when you are getting the carry, the sum is invalid and you have to add a 6. So to this number we are adding a 6. So here you are adding a 6. So 6 is nothing but 0, 1, 1, 0. 1 plus 0 is 1. 1 plus 0 is 1. 1 plus 0 is 1. Then 0 plus 0 is 0. So here you are having a 1. To the left you can add 3 zeros. What is 9 plus 8? 9 plus 8 is 17. The 17, when you are writing in BCD, how you can write? 0, 1, 1, 1. Here, this 1 you can write it as 0, 0, 0, 1. So while adding 9 plus 8, we are getting 17. So here you are having three cases. First one, when adding two binary numbers, the sum is less than or equal to 9, no modification is required. If you are adding two numbers, if the sum is greater than 9, you have to add 6. Similarly, when you are adding two BCD numbers, if you are getting a carry, then you have to add 6. Next, you have to add 24 plus 18 in BCD. So 24 plus 18. The answer what you have to got is 42. So 24. So binary value of 4 is 0, 1, 0, 0. Then binary value of 2 is 0, 0, 1, 0. So that we have written here. This is 4. This is 10. Sorry. This is 2. And 18 you have written. This is 8 and this is 1. Now what you are doing is you are adding this what this these two numbers. First 0 plus 0 is 0. Then 0 plus 0 is 0. 1. Then 1. So sum what you are getting while adding these two is 1, 1, 0, 0. So here while you are adding, what you are getting is 1, 1, 1, 0, 0. Or clearly I will write here. Here I will write the 0, 0, 1, 0. That is 2. And for 4, 0, 1, 0, 0. 1 is 0, 0, 0, 1. And this 8 is 1, 0, 0, 0. Now we are adding these two by ordinary binary addition. 0 plus 1, 0 plus 0 is 0. 0 plus 0 is 0. 1 plus 0 is 1. 0 plus 1 is 1. Here 1. 1 plus 0 is 1. Here 0, 0. So what is this number? This is 12. So this number is greater than 9. So what you have to do? You have to add a 6. So we are getting a 12, and this 12 to this 12 we have to add 6. So 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 1 is 1, 0. The 0 here, and this is the carry. Again 1 plus 1 is 1 0. You are having 0 here. Then we have to add the carry here. This is the carry. We are getting 1 0 here. We have returned the sum 0 and the carry 1 here. Then again 1 plus 1, 1 0. Again I have returned the carry here. So 1 plus 1, 1 0. Here I'll be getting a carry. So I have returned that carry here. So 0 is 0. So here you can, if you want, you can put zeros here, no problem. So finally we are getting, what is 0 0 1 0? It is 2. And what is 0 1 0 0? It is 4. So this is the answer. Once again I will tell it. Once again I am telling, we are going to add 24 plus 18. So in BCD we have to split each and we have to write each digit by 4-bit binary number. So the value of 4 is 0 1 0 0. The value of 2 is 0 0 1 0. Similarly, the value of 8 is 1 0 0 0 and the value of 1 is 0 0 0 1. Now we are going for ordinary binary addition. 0 plus 0 is 0, 0 plus 0 is 0, 1 plus 0 is 1, 0 plus 1 is 1. Then we are adding this one. 0 plus 1 is 1, 1 plus 0 is 1, 0 plus 0 is 0 and 0 plus 0 is 0. Now you consider this number. The value of this number is 1100. It is greater than 9. So in BCD addition, if you are getting a number greater than 9, then we have to add a 6. So we are writing this number here. We are writing this sum here, and since this number is greater than 9, we are adding 60110. So 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 1 is 1 0. The sum 1 we are writing, the sum 0 we are writing here, and the carry we are writing here. Again 1 plus 1 is 1 0. The sum we are writing here and the carry we are writing here. So here if you want you can put zeros for your convenience. You can, if you want you can put zeros here. Now 1 plus 1 plus 0, that is 1 0. Sum is 0 and carry is 1. Again 1 plus 1 plus 0. Sum is 0. Next we are going to see BCD subtraction. So first what we are going to do is, first we are finding the 9's complement of the negative number. Then we are adding the two numbers using BCD addition. If a carry is generated, we are adding the carry to the result. Otherwise, we are finding the 9's complement of the result. So in BCD subtraction, what we are doing is, first we are finding the 9's complement of the negative number. Then we are adding the negative number with the other number. Then if a carry is generated, we are adding the carry to the result. And otherwise, we are finding the 9's complement of the result. Now we are going to subtract 79 minus 26 using BCD. So first we are taking this 26. So for this 26, we are for this 26 we are finding the 9's complement. So we have to subtract each digit from 9. So 9 minus 6 is 3 and 9 minus 2 is 7. So we are getting 73. So we are adding this 73 with this 79 and we are getting a carry. So we are adding this carry to this number. So we are getting 53. So how we are doing is, first this is 79. This is 79 and this is 73. So actually what we are doing is, we are subtracting 79 minus, we are subtracting 79 minus 26. So what we have done is, first we have found out the nines complement of this 26. The nines complement of this 26 is nothing but 73. So after finding this nines complement, we are adding 79 and 73. So this is 79 and this is 73. So we are adding this by using ordinary binary addition. So what you are getting, 1 plus 1 is 1 0. Adding a carry, 1 plus 1 is 1 0. 1 plus 0 is 1. Then here you will be getting a 1. Similarly here 1 plus 1 is 1 0. 1 plus 1, here while adding these two, 1 plus 1 is 1 0 and we are having this carry is written here, so we'll be getting 1 plus 1 plus 1, that is 1 1. So again we are writing this 1 here, so carry 1 here, so 1 plus 1 plus 1, so 1 1. Again we are writing the carry here, so you'll be getting 1. So the sum what you are getting here is 1 1 1 0 and the sum what you are getting here is 1 1 0 0. So 1 1 1 0, this one, and here 1 1 0 0. So this number is 12. So it is greater than 9. We have to add a 6. So what you are doing, we are adding a 6 to this number. So while adding 6, what you will be getting, 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 1 is 1 0, 1 plus 1 is 1 0. So again we are adding this carry here. So here what will be getting, 1 plus 0 is 1. If you want, you can put zeros here. One plus 0 plus 0, 1. Then 1 plus 0, 1. Then 1 plus 0, 1. Then 1 plus 0, 1. So the sum what you are getting is this one. So 0, 1, 0, 0 and 1, 1, 0, 0. So this number is also greater than 9. So we are adding a 6. So we have to copy this number same like this. Then here only you have to add a 6. So 1 plus 0 is 1. Then 1 plus 1 is 1 0. You are writing the sum here and you are writing the carry here. 1 plus 1 plus 1, that is 1 1. You are writing the sum here and you are writing the carry here. So 1 plus 1 is 1 0. You are writing the sum here and you are writing the carry here. So here you are getting a carry. So you have to add this carry with this number. So 0 plus 1 is 1. 1 plus 0 is 1. 0 plus 0 is 0. 0 plus 0 is 0. I can same 0 1 0 0. So 79 minus 23 is sorry 79 minus 26. Actually 79 minus 26 is 9 minus 6 is 3 and 7 minus 2 is 5. So actually we have to get 53. So we are subtracting 79 minus 26 and we have to get 53. So this value is nothing but 3 and this value is nothing but 5. Totally we are getting 53. Again, once again I am telling this is 79 and this is 73. That is nothing but the 9's complement of 26. So we are adding these two. So we are getting the sum as 1110 and 1100. So while adding these two, we are getting this as the sum. So this sum is greater than 9. So we are adding a 6. While adding a 6, we are getting this as a sum and we are getting a carry and we are adding this carry with this number. So we are getting this number. So this is 15. So it is greater than 9. So again we have to add a 6. So we are adding a 6 and we are getting a carry here. So this carry again we are adding to this number. So we are getting 53. So 79 minus 26 is 53. So we have got the answer. Next we are going to add 184 plus 576 using Bcd addition. So this is 1, this is 8 and this is 4 and this is 5, 7, 6. First we are adding these two. So you are getting 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 1 is 1, 0. You'll be getting 0 here and carry 1. So this is the sum while adding these two. So while adding these two, you'll be getting 0 plus 1 is 1, 0 plus 1 is 1, 0 plus 1 is 1 and 1. This is the sum what you are getting. Then while adding this, you'll be getting this as the sum. 1 plus 1 is 0, sorry 1 0. So you'll be writing the carry. So this carry 1 plus the 0 will become 1 and 0 plus 1 is 1 and 0 plus 0 is 0. Now starting from here this number is greater than 9, so we are adding 6. So 0 plus 0 is 0, 1 plus 1 is 1 0, 1 plus 1 is 1 0, again 1 plus 1 is 1 0. So that carry we are writing here. Again 1 plus 1 is 1 0, 1 plus 1 is 1 0, 1 plus 1 is 1 0, 1 plus 1 is 1 0. We'll be getting a carry, we'll be writing the carry here. So I'll be adding here and we'll be getting 0 plus 1 is 1 and 1 plus 1 is 1, 1 plus 1 plus 0 is 1, 1 plus 0 is 1, 0 plus 0 is 0. So while adding 184 plus 576, we have to get 760. So here you are getting 0. Then since you are getting a carry here, here you have to add a 6. So you have got a 6 here. So since your while addition this carry we are taking this carry to here, so you are getting 7. So once again, I will explain faster. So while adding these three by using binary addition, you will be getting these three as sum. And first you take this number is greater than 9, so we are adding a 6. So while adding a 6, we are getting 0 here, and this carry will be propagated here, and here we are getting a 0 0 0 and a carry. So since we are getting a carry here, you have to add a 6. So after adding 6, you have to take this carry to here, and you have to add to this number. So here you are getting 0, here you are getting 6, and while adding here you are getting 7. So finally you are getting 7 6 0. So the things what you have to remember is, while adding two numbers, first you have to add the binary numbers. If you are getting a number greater than 9, you have to add 6. Or if you are adding two numbers, if you are getting a carry, then also you have to add 6. Okay, this is the answer. The main thing what you have to remember is, after adding 6, if you are getting a carry, you have to add that carry to the next BCD digit. So you got 760.